Okay, welcome to the presentation on diffraction. So the aim of this presentation is to use Huygens Principle to explain diffraction. Okay, so we looked at the ripple tank. This is a still taken from the ripple tank, which has been touched up to make it clearer what was happening. And we saw, although this picture isn't where you have optimum diffraction happening, it's close to it. When the gap size is close to the wavelength size, you get the most amount of diffraction. And what we saw was you got a wave coming in, and the wave itself would spread out, and you'd get these funny kind of interference patterns here where the wave was cancelling out, or the intensity of the wave was less. If you was to draw a graph of this, of the intensity of the wave, you get a minimum point, a maximum point, and a maximum point on the graph, and you get a pattern like shown here. So we need to use Huygens Principle to explain this. Why does this happen? Okay, so Huygens Principle states that a wavefront, and remember a wavefront is any point on a wave which is the same, like this line here or this line here, and the same in these circular lines as well, are wavefronts. You can consider it as a secondary source of spherical wavelets. So for instance, take it for example this line here. We could think of this as a load of spherical wavelets spreading out in the forward direction at the speed of light. Now it says the speed of light, so that's what applies to light, but if you're talking about in a ripple tank, it's the speed at which the waves would move in the ripple tank. The new wavefront is tangential to the surface of all the secondary wavelets. Okay, so let's try and understand this with an example. So firstly, what is a wavelet? Okay, so a wavelet is like a like if you was to drop a stone into water, you'd see a ripple spread out. Well, you could think of that as a wavelet. Okay, so here's a wavelet, and I'm going to, for the sake of simplicity, we're just going to say that the black lines will represent positive displacements. But if you remember from the definition of a wavefront, it's just an identical point on the wave at any point. So this could be the peak, and you could go along this line and find that the peak of the wave was always here. It may not be the peak though. But just to make this presentation simpler to understand and easier to understand, I'm going to stick with the black line is going to represent a positive displacement, and if you imagine then, if you was to go backwards, you'd eventually come to the point where you've got the trough of that displacement, or the negative displacement. So if you was to match it up with this picture here, the black line would be this positive displacement where the water is higher, and the blue line is representing where the water is lower, the trough. Okay, so that is a wavelet. How can we make a straight line out of a wavelet? If we put many wavelets together, you start to see that these positive displacements will be adding up with the other positive displacements all here. Okay, and the positive displacements will be cancelling out with the troughs or the negative displacements of the other wavelets here. Or you could think of it as the troughs will be all adding up here. So the more you get, the more you can basically replace this complicated picture with a simple picture of, here is the positive displacement of the wave, or the peak, and here's the trough of the wave. So that's it simplified. So let's look at modelling a plane wave. So this would be like the ripples in the ripple tank moving forward from the beam that's bouncing up and down. Now let's replace the line by many wavelets. Okay, so I'm just showing one line for each wavelet. You can imagine that if this was the positive part, then the negative part of the displacement would be somewhere about here as well. Okay, and you can see that pretty much they would form a new line, and you could do an infinite number of wavelets. You could do 1,000 little dots and across here, and they clearly would make up a flat line, then a straight line. Okay, and then the wavelets would grow. You know, you could drop a pebble into water, and you'd watch a wavelet grow and grow and grow, and you basically have achieved the same thing as just drawing a straight line each wavelet. Okay, so let's have a look at actually how this explains diffraction. So we saw it in the ripple tank. The ripples come towards a barrier, and there's a hole in the barrier, and around the edges of that hole you get diffraction. It's actually, you can see that this wave would be spreading out. Now remember, we could model this with many more points, and you'd get a clearer, more accurate picture of what really happens. Okay, and as these wavelets grow, you get some interesting things happening. I think it's pretty clear to see that here you're going to have very strongly reinforcing and a high amplitude of wave, and the same here, here, and maybe around here it's going to be a little bit messed up, not quite reinforcing. In other areas you can see that this black line, the purple line or the red line at some point is going to be falling. So this, let's just imagine it was positive displacement, it would be falling into the negative displacement of the black wavelet. So these two would really be cancelling each other out. Similarly, you could say that the green line is falling into maybe the purple lines, well, a little bit anyway. You're going to get negative displacement, sorry, you're going to get it's going to be cancelling itself out here, and it's going to be adding up here, here, and here. So you're going to get a similar kind of pattern. So you can see already Huygens Principle does quite a good job of explaining some of this. It also helps us understand why, if the gap size is identical to the wavelength, you get maximum diffraction. So if we model it here, okay, and the reason I've just done these as different colours is just to make it easier to interpret the pictures. It's not intrinsic to the principle. Okay, so on the first step you can see you're getting maximum displacement here, and you can see that the green line is going to add up with the red line on both sides, so that's also going to be positive displacement. Let's just keep the model going. Okay, and if we analyse here, you can see clearly that the orange, the green and the red are all going to add up, so a bigger wave. Okay, so this line is just what you'd have in this plane. Okay, so you get maximum amplitude here. Let's choose another point on the side and take that line and put it across here, and then analyse the waves, what's going to happen to them. Okay, now it's a bit hard to see what's going on here, but you could, for instance, take the green and the yellow line, add them up, and you can see that because they're together like this, that the purple line replaces the green and the yellow line. Okay, and now these are going to cancel each other out, but because the purple line is slightly bigger than the red line, you're still going to have some displacement. Okay, and then let's take this part. Okay, so you can see clearly that the red and the yellow are going to cancel each other out exactly, and you just be left with the amplitude of the green line. So you're going to still get some variation in the amplitude as you go around, but you're going to get the most diffraction happening when the wave size is the same size as the gap that it's moving through. Okay, so let's just look at this with when you make the wavelength smaller than the gap size. Okay, and you get less diffraction. You get a lot of reinforcement here, and you start to see you're going to be getting cancelling out here as the lines aren't on top of each other. Okay, let's just make it a bit closer. Okay, and again, this is when you get the wavelength is getting closer towards the gap size, and you are starting to get constructive interference here, and obviously it's all constructive here, and there will be some cancelling out around these kind of areas. You can see that the orange line here is falling into the gap of the green line, so this would be in the negative displacement of the green line's wave, and it would be cancelling it out at that point there. So you'd be getting interference. Okay, so this is true in water waves, and this is a great way of looking at light.
Okay, so what I'm actually going to do now is make a really small hole in a piece of tinfoil so that we can see some diffraction effects happening. If you take a pin and you actually puncture the tinfoil, and I don't know if you can actually see this, possibly you can, that hole will be way too big. But if I take the pin and I put it on something hard, like a ceramic plate, and I just push it into the plate, maybe give it a little twist. I'm just going to do that one more time. I slightly tore the tinfoil. And the hole will be so small you'll lose it unless you draw around it. I've now produced a hole small enough to show the effects of diffraction. Okay, so I'm just going to attempt to show you just how small the dot is you need to make. Here's the dot I made by puncturing that's this one here. I just punctured it with a needle, and the dot here, if the camera just gets focused, you can just about see there's a tiny dot in the centre of that circle. What I'm going to do is use my presenting wand or whatever for when I'm doing PowerPoint in class, and fire a laser at the tiny little hole, and we'll see what comes through on the other side on a screen.
Is light a wave? What I've shown already is to do an experiment using a pinhole and a red laser light, and then take some very slow photography of it to try and get the resolution of the picture out. And this is what I got. Okay. After many attempts, it wasn't easy actually to get this picture, because you have to set up the camera perfectly in order to do it. But anyway, you've got something going on here. Now, because my picture isn't great, you can definitely see if this was just one hole, how come there's this ring around the outside of it? How come there isn't just one splodge in the middle? And the reason is because light is being diffracted, because light is a wave, or has wave-like behavior anyway. This is a photo taken from Hyperphysics, and they've obviously spent a lot of time and effort doing this. And I read on the site that they made many pinholes, and they worked through them, and they found the best one. And you can clearly see many areas where you're getting constructive interference, and then the bright central spot. If you look at just the center of that picture, you're basically getting a diffraction pattern, and it's the same thing. Okay, so we can extend this idea further, and it turns out you can really express this in a very simple way. If you imagine a wave coming in this direction, and you've got a gap here, you can make some assumptions, that the medium is uniform, because obviously if this was in water, if the water got shallower, the wavelength would change. We're also assuming that the wavefronts are in line, and this becomes important with light. That's why we use laser light, because laser light, all the waves are in the same, they're all in line with each other basically. Okay, and also for this idea to work, the distance to the screen has to be large compared to the slit size, so that that just makes the calculations a lot easier. And also, we did see that when you're looking at diffraction, early on the pattern doesn't quite emerge. You have to move a bit further out for the pattern to become repeatable and clear. Anyway, so we can imagine that a wavefront moving from here and a wavefront moving from here, if it's a long distance, because this little section here is forming a triangle, this wave would have travelled a little bit further than this wave, which means that you have an opportunity for those waves to either constructively or destructively interfere. Now this is where the assumptions come in. If we assume that it's a long way from the gap size, if we assume that it's a long way away to the wall where the wave is going to be shown or screen, then you can pretty much assume that these lines are parallel. If these lines are parallel, then this angle will be equal to this angle here. Now it's totally arbitrary. We didn't have to choose a distance of half of the gap size, which we're going to be calling B. But if it's a simple enough place to choose, and it means that you've got numbers that are easy to work with. So anyway, this distance would be half B. This is a right angle triangle. If this is half the wavelength, then the waves are going to be exactly out of phase, and you're going to get cancelling out. So you can find the first minimum in the diffraction pattern, what angle it will occur anyway, from the central line, just by doing a little bit of trigonometry. So this is the hypotenuse, this is the opposite. We're using the hypotenuse and the opposite, so we're using sine theta, opposite of hypotenuse, or lambda over 2 over b over 2, which simplifies down to sine theta is equal to lambda over b. This is where you'll find destructive interference. And it shouldn't be really too much of a surprise that constructive interference would be 2b, because we're just basically saying that this is now just lambda, one wave out. When you're out by exactly one wave, the waves will start adding up with each other again, and you'll get constructive interference. Okay, so these two formulas can be used to do all these calculations for simple diffraction. Okay, so this has implications for speaker design. This is a subwoofer. It's used for bass. the bassy noises you get in like drum beats and stuff. And it's got a large aperture, and that large aperture means it's closer to the wavelength of the actual sound, and you get more diffraction. Tweeters, on the other hand, the waves are very small, higher pitched sounds, and because the waves are small, you need a small aperture to create the most diffraction, so that everybody in the room can hear the sound. Okay, so again, you can see it's quite common design that you get the size of the speaker can tell you what kind of frequency range is going to be coming out of it, because that's how they're designed. Okay, so if you pause the video and read this example question and have an attempt at it as well. Okay, so I'm going to go through this question. So we've got a speaker here. It's playing some music, some drum and bass, which is very bassy, with a frequency range of 100 to 3000 Hertz. It says to take the average and calculate whether each ear is going to have the same kind of experience, basically. I've got a couple of key numbers. The distance is 2 meters. They're a meter apart, the ears are. The speaker's aperture size is 50 centimeters or half a meter. Okay. The speed of sound here has been given to us as well on that day. The speed will change depending on the day and the temperature of the air and pressure and such. So what we aim to do then is to work out where the first minimum will appear because of the diffraction, and see if it's anywhere near this ear. Okay, so step one, let's get all the information collated. Speed of sound, frequency, well, it said to take the average, so we had 1000 Hertz and 3000 Hertz, add them together, divide by 2, 2000 Hertz. The gap size was 0.5 meters. I'm basically using this equation. I'm actually missing the wavelength, but obviously I can use the speed of sound and the frequency. So V is equal to F lambda, rearrange for lambda is going to give me V over F, 340 over 2000, 0.7 meters, sorry, 0.17 meters is the wavelength of that wave on average. Okay, so if you had a perfectly designed speaker for that music, it would have a diameter of exactly 0.17 meters. That wasn't the case. The diameter was 0.5 meters. So what we shall do now is look at where the first minimum will occur. Okay, so we've got sine. We're going to be using this equation and substituting the numbers into it. Lambda over the gap size, or the size of the aperture, and just this number divided by this number gets us to 0.34. Taking the inverse sine of both sides gets us 19.9 degrees. So, just to go back to the diagram, if you measured an angle of 19.9 degrees and drew a straight line, that's exactly where you'd be hearing less sound. It would be much quieter. Alright, so let's just get back to where we were. So now we need to do a diagram and work out whether the outside ear can hear as well as the central one. Okay, so if this is 2 meters and this is 1 meter, so the central ear was here and the outside ear was here, what angle will this be? So again, we just use this time we're going to be using the opposite and the adjacent. That's tan. So tan theta is equal to a half inverse of take the inverse of tan of both sides, and we get 26.5 degrees. So basically, we're going to be pretty close to a minimum if you're here. Okay, the minimum would be occurring a bit down here. So really, in the answer to the question, it wouldn't be having as good a time as the central ear. The person listening over here would be hearing degraded sound. It wouldn't be as loud. Okay, so thank you very much for watching. I hope you've enjoyed this, and remember to subscribe, like and share.
Hi there. During this session I'm going to be talking about the wave phenomena of diffraction, specifically single slit diffraction. Now what single slit diffraction is the interference of a source of light with itself. In this case it's light coming from one single slit. I've got two examples of what this light would look like if it was projected onto a screen. The top example in green shows what happens when you have monochromatic, so single wavelength light, in this case, reflecting green. And what we can see is, rather than just having a single slit projected onto the screen in front of us, we get a pattern of what are known as fringes as I go out. So we have a central peak of high intensity, and then we have a darkened area, and then we have another fringe, then a darkened area, fringe, darkened area, fringe. And this process repeats on both sides. And it comes out due to, as we're going to see later on, the interference of light from one side of the slit to the other side of the slit. Now, the diagram below shows this happening with white light. And the reason it's interesting is because you can see that we get a color distinction taking place as we move away from the central slit. And the reason we get that color distinction is because this rule is wavelength dependent. Okay, so depending on the wavelength depends on the diffraction or the location of diffraction, crucially. So let's think about this a little bit more visually about what's actually happening here. So what I have is a single light source, and this source is projecting towards a slit. Now this slit produces monochromatic light. Perfect. Now, as we know from the idea of Huygens Principle, at every single point in this slit we get a wavelet, so we get light being projected in circular motion. And what happens is if we take this light and allow it to project out to a screen at a set distance away, we get situations of having both constructive interference, that we get the bright areas, and we get destructive interference, where we get the dark areas. A really important graph which you're going to have to be able to produce would be the angle away from the center and the intensity distribution curve. So this curve on the far right hand side is something that you're going to have to reproduce. Now what this shows is that bright central area, and then it shows how the intensity dips away as we see fringes, and this carries on further and further. The further out the fringes are, the less the intensity, until we can't make out these at all. Starting over, the distance between the edge of the slit and position Y is seen to be that of one wavelength. Okay. The distance between Y and point P is equal to the distance between the other edge of the slit and point P. Now you may be thinking that seems strange. If it's one wavelength difference, surely that would cause them to be constructive interference. However, we've got to remember about all of the other light which is reaching this point. And as it turns out, if we have this situation, the average difference, so in the center here, is actually only half a wavelength. And if it's half a wavelength difference, that causes destructive interference. Now, if I look at the angles here, as it happens, my first angle, angle θ1, is equal to the distance, wavelength of the light divided by b. This is given by IB, so this is the standard statement. Now, as it happens, angle 2 is equal to, or using the small angle approximation, is equal to f divided by d. F is the distance between the slit and the screen divided by d. Now as it happens, angle 1 and angle 2, due to small angle approximation, can be considered to be the same value, which is why I haven't got 1 and 2 subscripted on these two features. Now that means that you can therefore work out that the distance between the central maximum and the first minimum should be equal to the multiplication of the distance to the screen multiplied by the wavelength of the light divided by the width of the slit. Now you're not given this by the IB. You're given the earlier value, so you always have to think about that, and you'd have to explain it potentially using a diagram. Okay. So let's put this into practice. I've got an example question here. Light from a laser is used to form a single slit diffraction pattern. The width of the slit is 0.1 millimeters, and the screen is 3 meters away from the slit. The width of the central maximum is measured to be 2.6 centimeters. What is the wavelength of the laser? So take a moment, try and answer this question. Now I'm going to show you the solution. The answer goes, since the screen is a long way away from the slit, we can use small angle approximation to recognize that D equals F multiplied by the wavelength divided by B. Okay. This means that F is the distance from the slit to the screen. That's going to be 3 meters. The half width of the center maximum is going to be 1.3 centimeters. So that's going to be the value D, the distance from the middle to the first minimum. Therefore, we can put in the values or work out what the wavelength is from known values which we've been given. So we know what D is. We know what B is going to be. We know what the value for B is. We know the value for D is. We know what the value for the wavelength for F is. So if I put all these numbers in, I get 430 nanometers, which is the wavelength of the light which produced this situation. Okay. Hopefully, that's pretty much the example question which is going to come up in any exam. So as long as you're confident with explaining what's happening, showing this diagrammatically, and answer any questions, you shouldn't have any problems with this in the future.